In today's session, that we learn about how to design a 3-bit synchronous up counter and down counter. In last session, we learned about 2-bit synchronous counter, how to design it up counter as well as the down counter. The same procedure we are going to follow here too. Only the difference is we are going to add one more flip-flop to design a 3-bit up counter or a down counter. Since it is a 3-bit, so we have to use your number of flip-flops are 3. So now let me design your circuit with using your JK flip-flop. So type of flip-flop is also JK flip-flop to design your up counter. Now next step is to draw the logical diagram of your counter. Since it is having 3 flip-flops, so we are going to have number of states are increased with 8. So now if you have two flip-flops, 2 square is 4 states. If you have a 3 flip-flop, you can have your 8 states. So in those 8 states are 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Upon having the last state, which is your 1 1, it comes back to its initial state, which is 0 0 0. So this type of up counter, just if I am just observing, so the equivalent code, so for initial state is 0, it is decimal code is 0, next state is 1. So and here if your present state is 1, next state is a 0. So if I observe the successive state difference, so we have a 1 is the difference between the successive states. Hence, so upon giving the clock pulse, your previous states are incremented by logic 1. Hence, it is known as your up counter. Now, upon drawing that logic diagram, then we are going to draw the excitation table using the excitation table of your JK flip-flop. So this is a 3-bit counter or your mod 8 counter state diagram. So initial state is 0, 1, 2, 3, then 4. If my present state is 4, next state is 5. If my present state is 5, next state is 6. If my present state is 6, next state is 7. If my present state is 7, which is the last state, so then the next state will be your initial state, which is 0 0. So now according to that, we wrote here present state and next states in your excitation table. QC, QB, QA denotes your present state. QC star, QC plus 1, QB plus 1, QA plus 1 denotes your next state. JC, KC, JB, KB, as well as JA, KA are the corresponding inputs of your JK flip-flop, 3 flip-flop inputs. Now, upon writing here the state transition, so initial state 0, next state is 1. If you have my present state is 1, next state is 2. If my present state is 2, next state is 3. If my present state is 3, next state is 4. If my present state is 4, next state is 5. If my present state is 5, next state is 6. If my present state is 6, next state is 7. If my present state is 1 1, so it is a binary number of 7. 1 1, next state must be your 0 state. So final state of your 3-bit counter is 1 1 1. Now, if that is my present state, next state is your initial state, which is come back as your next state in your 3-bit counter, so which is 0 0 0. Now, based on your state transition from present state to next state, QC, QC plus 1, we are going to determine. So by comparing QC, QC plus 1 in every clock pulse, we are going to write your JC value as well as your KC value using this excitation table of JK 0 to 0, 0 don't care, 0 to 1, 1 don't care, 1 to 0, don't care 1, 1 to 1, don't care 0. So now first let me write your JC KC values. QC and QC plus 1 are 0 0. Hence here 0 don't care. So 0 0 is your QC QC plus 1 for second clock pulse. So 0 don't care. Third clock pulse 0 0. Hence 0 don't care. Next fourth clock pulse. So 0 1. So hence 1 don't care. Next fifth clock pulse 1 1. So here don't care 0. 6 clock plus 1 1, so don't care 0, 1 1, so don't care 0, so 1 1 1 and 0, which is don't care 1. So upon writing all these values of JC, KC, JB, KB, so JB, KB is written based on your QB and QB plus 1 transition. So 0 0, we are going to write 0 don't care, 0 to 1, 1 don't care, like this. So we are going to write here all the values of your corresponding excitation inputs using this excitation table. Upon writing that, so standard SOP expressions are JC is equal to only on your, just by searching the minterm values on your JC column, only one minterm which is on present states, so 0 1 1 through 3. So and your 4 don't case, 4, 5, 6, 7 are the don't case. So case is equal to sigma m of only one minterm is available on 7 and the remaining are your don't case. So 0 to 3 are the don't case. So we wrote that expressions of SSOP. JB is equal to 1 comma 5 are the minterms, 4 are the don't case. So sigma D of 2, 3, 6, 7. KB is equal to 2 minterms are there. 2 minterms on your 3 as well as on 7 and your don't case are on KB 0, 1 as well as your 4 and 5. So next JA. So alternatively we have your minterms and don't case of when I compare with your KA. So JA is 0, 2, 4, 6 are the minterms. 1, 3, 5, 7 are the don't case. KA is 1, 3, 5, 7 are the minterm. 2, 0, 2, 4, 6 are the don't case. Now using these Boolean expressions of standard SOP, let me minimize your each function. Upon minimizing a function, JA, KA equal to logic 1, JB, KB equal to QA, JC, KC equal to QB and QA. So now here JA, KA, so including your don't case as your minterm, so we can have your logical one. So JA, KA equal to JB, KB equal to QA, JC equal to QB into QA, KC equal to QB into QA. So we have the product terms JC, KC equal to QB, QA, JB, QB equal to QA, JA, KA is equal to logic 1. Now let me take the 3 flip-flops. So A flip-flop will be the least significant bit and C flip-flop will be the most significant bit. So JA, KA are connected to logical 1, JB, KB are connected to the QA present state and JC, KC are connected to QB and QA. So now we are going to draw the logical diagram of your counter by taking the 3 flip-flops. So now these 3 flip-flops logical diagram is based on your expressions or minimal expressions which we got. So since you are having your JK flip-flop, so clock pulse has taken as common and then we applied your JA, KA is high, JB, KB is connected with the previous state of your QA and JC is connected with the present state of your QA and QB ANDed with that using a one AND gate and AND gate output is connected as your JC. So now it can function like a up counter by giving the clock pulses, it can count it here in a up sequence. So how it counts, that we are going to verify now. So initially let me clear your QA, QB, QC as zeros. So upon clearing those all zeros, now for the first clock pulse, so negative edge, trailing edge, so your QA value is significant bit. JA, KA inputs are logic 1, hence the previous state is 0, it will toggle to logic 1. For every negative clock edge, your least significant flip-flop will be toggled from your present state to the next state. So second clock pulse, previous state is 1, so hence next state must be your 0 state. So the third clock pulse, present state is 0, hence it will move to the logical 1. Fourth clock pulse, present state is 1, so it will move to the logical 0. So for every clock pulse, your least significant bit will be toggled. Next, QB is toggled based on your QA output. So when it comes a negative edge on your first flip-flop or the least significant bit. So now QB is, so here we got your negative edge. So since your negative edge of your first clock pulse, so since your QB also synchronized, but your QE doesn't have your negative edge here, so previous state is continued as your 0. Next, on your second clock pulse, so your QA is logical 1, so hence your second flip-flop obtain your JB, KB inputs are equal to logical 1, hence your previous state 0 is now toggled to the logical 1 state on your QA. So for every negative edge of your QA, your state of the second flip-flop or the QB is toggled. So now here we obtain from 0 to 1, then 1 to 0, again 0 to 1 like that. So now next QC, last flip-flop will be toggled if and only if KB, QB and QA present states are both are at logical 1 state. So now we will check the state where that on which clock pulse so your QB and QA become logical. So first clock pulse both are zeros. On your second clock pulse, so here 0 1. Third clock pulse it is 1 1 1. So in your third clock pulse, so here 0 1. 0 is on QA, 1 is on QB. And fourth clock pulse, so previous states are both are logical ones, hence so when it comes to your fourth clock pulse, your state of the third flip-flop will toggle from 0 to 1, and then this state is continued till you get your next clock edge on your QB. So next clock edge on your QB along with QA is logic 1, so is obtained at your 8th clock pulse. There your output of your QC or your C flip-flop will toggle from 1 to 0 like this. So first flip-flop toggling is based on your clock, second flip-flop toggling is based on your first flip-flop, and third flip-flop toggling is based on your second flip-flop, but all will be operated on your common clock signal. Since of that their inputs which are transmitted from your previous flip-flops, you obtain the up sequence. So initially we have here on your initial, so which is 0, so first clock edge, so first clock pulse 0 0 1, and second clock pulse which is, so on your second clock pulse we have here 0 1 0, third clock pulse which is here 0 1 1. So next fourth clock pulse, so 1 0 0, fifth clock pulse you have 1 0 1, sixth clock pulse you have 1 1 0, seventh clock pulse you have all the three states of your flip-flops are 1 1 1. So now by just observing your successive states, so you have a difference of 1 in between the states after every one clock pulse, so hence it comes under your up counter. Now let me design your down counter of 3-bit 2. So in designing your 3-bit counter, so let me prefer a T flip-flop so to construct. So it is also a 3-bit counter, so we will going to use 3 flip-flops. From that we can obtain your 8 states. So initial state is 0, 7 is your first, after giving your first clock pulse you will obtain your maximum count, which is obtained from a 3-bit counter is 7, then 6 5 4 3 2 1 0. So based on this state diagram, let me draw the excitation table of present state, next state, and their excitation inputs using your excitation table of your toggle flip-flop. Since I preferred here toggle flip-flop, so if your present state is toggle in your at your next state, so then the toggle input is 1. If your present state is continued as your next state, toggle input is 0. So based on that we wrote here toggle flip-flop inputs of T3, third flip-flop, T2 is your second flip-flop, and T1 is your least significant bit. So now upon writing this, so T1 is 1, so K map, so if I am using your K map, and this is a 3 variable function, so hence here, so your outputs depends not only on Q1, Q2, but also depends on your Q3. So total number of cells are 8 cells we have here. So using that 8 cells K-map method, we are going to find your minimal expression. Now here upon mapping your T3, so only 2 minterms are there. So when it forms a pair, so it will give you Q2 bar, Q1 bar. So T2 or the second flip-flop excitation input in terms of your present state is equal to Q1 bar as it is having 4 minterms. So these two are arranged at your edges, left edge and your right edge. So both 2 and this 2, right edge and left edge minterms can form a quad, so which can give you the minimal expression which is equal to Q1 bar. Next, T1 is your least significant bit, so which is having all ones. So 8 ones are there. So 8 ones can form octet, and in a 3 variable came up, if you have 8 cells or ones, so then it is known to be the logical one. The remaining expression is logical one. Hence, the least significant toggle flip-flop input is connected to logic 1. Next, the second flip-flop T2 is connected with complement of your least significant flip-flop output is taken as your present state, and your T3 is equal to Q2 bar into Q1 bar. So upon designing this, so let me verify the timing diagram of your counter using your clock signal. So first clock pulse Q1 and Q2, Q3 all are reset to 0. Hence it will give you 0 outputs. So Q1, Q2, Q3 all are giving 0 outputs. Upon giving the first clock pulse, Q1 will be toggled for every clock edge. So hence for every clock edge, if my present state is 0, next state become 1, second clock pulse 1 to 0, third clock pulse 0 to 1. So for every clock negative edges or trailing edge, your flip-flop 1 or the least significant bit will be toggled. Next, we have taken the complement of your first flip-flop. Q1 is exactly complement to your flip-flop 1 output. So if it is 0, you will obtain logical 1. If it is 1, you obtain your logical. Q1 is 1, you obtain your logical 0 on your Q1 bar. Now, your Q2 output depends on your complemented state. So now as you have your negative edge on your Q1 bar, so my present state is 0, now it will be toggled to logic 1. So every negative edge of your second flip-flop can toggle your, first flip-flop can toggle your second flip-flop. So now second clock edge, so since my previous state is at logical 1 and my input to that applied flip-flop is Q1 bar is logical 0, hence it may not be toggled, so it will continue its previous state as your present state. But when I am coming to your third clock pulse falling edge, so third clock pulse falling edge, your Q1 bar is logical 1. So now your Q1 bar is applied as your TB, so T2, so hence so it will fall to the logical 0. So for every negative edge of your complemented state of first flip-flop, your second flip-flop output will be toggled. So now till that, so it will maintain its previous state as its next state. So 0 0. Next clock edge, so it will come to your 1 1. So like this, so it will toggle, but your last flip-flop, so last flip-flop will be toggled if complementary state of second flip-flop and first flip-flop both are logical, or logical on your trailing edges of your Q2 bar and Q1 bar only it will be toggled. So Q2 bar is now it will be toggled, as well as Q1 bar is also going to the falling edge at that state. So your present state of your third flip-flop will be toggled from 0 to 1, and till you get your next falling edge on your Q2 bar as well as on your Q1 bar, where these two are going on to the 0. So as T3 is equal to Q2 bar into Q1 bar. So if those two are at trailing edge, 0 bar become, so 1 end of 1, so which is equal to 1. So hence, so this T3 input is 1 if and only if your complementary state of your first flip-flop and second flip-flop are equal to logic 1. So hence here, so at that instant only, so it will toggle to the next level with a 0. So till that it will maintain to the same state. So 1 1 are my states before your toggling. So again after the fifth clock pulse, so you obtain a state, so where Q1 bar is going in a negative edge and as well as Q2 bar is also on a negative edge. So at that state, so your present state of 1, now it is toggled to the 0 state. So now for the first clock pulse, your state of the flip-flop is Q2 is 0 0 initial state. Next first clock pulse, so your state of Q1 is 1, Q2 is 1, Q3 is 1, 7. Next second clock pulse trailing edge, Q1 0, Q2 is 1, Q3 is 1, so 6. Third clock pulse it is 1 0 1, fourth clock pulse it is 1 0 0, fifth clock pulse it is 0 1 1 3. 6th clock pulse it is 0 1 0 2, 7th clock pulse it is 0 0 1, and upon reaching the 8th clock pulse it comes back to its initial state which is 0 0. So like this we have to design your counter.